Our project is about the implementation of MESIF in Gem5. In a shared memory multiprocessor system, local caches are used to reduce memory access latency and network traffic. Such systems usually support the caching of both shared and private data. Private data are used by a single processor. Shared data are used by multiple processors, essentially providing communication among the processors through reads and writes of the shared data. When shared data are cached, the shared value may be replicated in multiple caches. This replication reduces the access latency and memory bandwidth, but introduces a new problem called the cache coherency problem. That is, the view of memory held by two different processors is through their individual caches. Therefore, if proper precautions are not taken, both the processors could end up seeing two different values. This difficulty is generally referred to as the cache coherency problem. Let's say, for example, in a multi-core system where there are 4 cores, core 1, 2 and 3. Let's say core 1 and 2 are operating on the same variable x. Therefore, the value of x in core 1, 2 and main memory will be the same. Now, let's say any one of the two cores, core 1 or core 2, writes a new value to that variable. This new value must be reflected in the other core as well as in the main memory. So this is how we maintain cache coherency in a multi-core system. Thus, in a multi-core system where some level of caching may be shared while some levels are private, the coherence problem still exists and must be solved. This is the motivation behind choosing this topic. So in our project, we took MESI 2-level protocol as the base protocol and extended it to include the forward state. L1 term in our project indicates the private caches that are local to each processor, whereas the terms L2 and LLC are used interchangeably and they both refer to the shared last level cache. So in MESI, the E state indicates that a cache block is resident only in a single L1 cache, but it has a clean copy of it. The M state indicates that the block has been modified by a particular cache and that it exists only in that cache, but the copy in the main memory or the LLC is out of date. So in MESI, when there is an attempt to share a block in the exclusive state, only the LLC provides the requested data, even though the data is available in another L1 cache. We know that the access latency of L2 is greater than that of L1. Thus, it will be beneficial if another L1 that has the requested data in its local cache could satisfy the request and directly deliver the data to requester. This leads to an extension of the MESI protocol to include the forward state. This state designates which sharing processor should respond to the request. MESIF was originally developed for Snoopy-based coherence protocols by Intel, but it is applicable for directory-based protocols as well, and it is called as Home Snoop. To better explain forward state with the help of an example, let's consider a 3-core system L10, where L10, L11 and L12 are the local caches and L2 is the shared last level cache. So let's say that L11 and L12 have the data that is being requested by L10. That is, both L11 and L12 are in the shared state. Even though they contain the data that is being requested by L10, in MESI protocol, the request for data is sent to L2 cache, that is the last level cache, and L2 will service the request. GetS is the coherence request that is always generated when an L1 cache wants to get a read-only copy of the data. So in MESI, even though L11 and L12 have the data, L2 will only service the request. This increases the response time for a request. Whereas in MESIF, one of the sharers will be in the forward state F, and this request will be serviced by the forwarder. Therefore, the requester will issue a GetS request to L2, and L2 will intimate the forwarder to transfer the data directly to the requester. We implemented this forward GetS coherence request, which initiates the transfer of data from forwarder to the requester. This reduces the response time greatly. So for each block, a table is maintained in L2 which stores information about the sharers list, forward and the exclusive owner. So let's understand or analyze the contents of this table based on the previous example. Before the getter's request was issued from L10, this is the content of the table wherein the cache state indicates the state of the L2 cache. Since there are multiple sharers for this block, the cache state is indicated as SS, which means shared. And L11 is being assigned as the forwarder, which means that this L11 is responsible for servicing getter's requests. After the getter's request was serviced by L2, the contents of the table are changed to reflect the addition of L10 in the sharers list. And now L10 is assigned as the new forwarder, which means that in the future, getter's requests will be serviced by L10. One more aspect in GEM5 is silent eviction. That is, when an L1 cache is replacing its block, it is not communicated to L2. So thus the sharers list need not be accurate in MESI at all points of time. The advantage of silent eviction is that it reduces network traffic, but this scheme does not work well with MESIF. Therefore, we implemented explicit eviction where each L1 replacement is communicated and the corresponding entry in the table is updated. So there are two basic reasons for implementing explicit eviction. When a block in the forward state is replaced, we have to assign a new forwarder for that block. We can actually properly assign a new forwarder only if the sharers list is properly maintained. Similarly, when a block is replaced from one of the sharers, it should be communicated to L2 and L2 should remove the corresponding cache from sharers list. This ensures that we do not assign forward state wrongly to a non-sharing cache in the future. So according to the previous example, after L10 replaces its block, the cache state of L2 is still maintained in SS because there are two caches that share the same block, but L10 is removed from the table, from the sharers list of the table, and one of the two sharers is being assigned as the new forwarder. In this case, L11 is assigned as the new forwarder, and L11 will be responsible for future getters requests for the same block.
Now we will be talking about MESI L1 controller state diagram. So the green circles denotes the stable states and the red circle denotes the transient states. And all these are events which corresponds to the transitions. So on happening one event, we will transition from one state to other state. So the stable states are M, E, S, and I. I corresponds to invalid. S correspond to share, which means two or more cache blocks have the same data in clean state. E means exclusive, which means only one of the cache has the data cache block, which is in clean state. And M means modified, which means only exactly one L1 cache has the data and the data block is dirty. So this is basic description of the state diagram for MESI. Now we will be talking about changes which we have introduced in the state diagram for MESIF, that is to support the forward state. So most of the states are same, transient states. We have introduced two new states called as F and IF. F is very similar to S state. It's just that the new name for the cache block in shared state, which will be used to support the requests coming from L1 cache for shared data. So in the previous MESI implementation, the L2 cache will be forwarding the data to the requester, but in the MESIF, the F state block will be forwarding the data to requester in the case of when there is a need of shared data block in any of the L1 caches. So as you can see, there is no transition from I to S state in this. Rather, we will be going from IF to F state whenever there is the load or I fetch, depending on if other L1 caches have the same block. So whenever there is a load or I fetch comes, we moves to IF state, and we wait there to receive the other L1 caches responses to know that whether other L1 cache block other L1 caches has this block. If the other L1 caches have the same block, then we will move to F state, which is a shared state, but this new guy who have requested for the data recently will become the F state. And if none of the L1 caches has the data, then we will move to E state, which is exclusive state. Now let's talk about the messy L2 controller state diagram. Similarly here also the green circles denotes the stable state and the red circle denotes the transient state. So here also we have four stable states, which is SS, NP, M and MT. SS basically denotes the shared state, which means that two or more L1 caches has the same data and clean copy of it. NP is the invalid state, which means the L2 doesn't have the cache block, which is, so it's basically the I state in the messy state diagram. M is denotes basically is that L2 cache block has the data, but none of the L1 caches has this block. MT denotes that L2 has the data, which could be in either exclusive state or modified state, which means exactly one of the L1 cache has this data, which could be either in exclusive or modified state. So let's move to what changes we have proposed in MESIF L2 controller. So we want to now support the forward state. Now in this case, the L2 will not respond to any shared request for shared data from L1 cache, but it will forward the request to forwarder L1 cache, which will eventually send the data to L1 cache who is requesting for this. So in order to support this, we have introduced one more state, transient state, which is SSMBTR. So whenever there is a SS block, shared block, which gets the L1 getX request, we will move to SSMBTR state and we will forward the request to forwarder guy to send the data to requester, and we will wait in this state until we get an unblock signal from the requester saying that it has received the data. Now also there is a change in this path, which is L1 getX and L1 update. Similarly here also previously the L2 cache used to send the data to L1 cache directly, but now since we have the forward state, in this path, along this path, we will also send the data, we will also send the request new L1 getX or L1 update request to the forwarder guy to forward the data to requester, and we will move to SSMB state, and we will wait in this state until we get exclusive unblock from the requester saying that we have received, that the requester has received the data, and we will move to empty state. Since we are not supporting silent eviction in this case, we will have to handle the L1 replace request coming from L1 caches. Thus, based on our current sharers count, we will either move to empty state or we will move from empty state to M state. So there are new transitions introduced from SS to empty and M, which we will be explaining in next slides in detail.
Since we support explicit or non-silent eviction, we made several changes to the L2 controller. This portion of state machine shows some of the relevant states of L2. When the L2 block is in the SS state, it means that more than one L1 caches have that block. When the L2 block is in the empty state, it means that this block is present in exactly one L1 cache, either as a clean copy or as a modified copy. M state means that no L1 cache has it and only L2 cache has it. Now, when a forward block is replaced in SS state, we need to find a new forwarder who will take care of future getS and getX requests. This is done during the move to SS forward path, and this is possible since we have an exact sharer list and forwarder information because of explicit evictions. But this forward state should not be found when there are exactly two sharers, because in that case, after replacement, only one cache would have it in the exclusive state. This is denoted by the transition through the move to empty path, and in this case L2 moves from SS to empty state. Similarly, when a non-forward cache is replaced, we do not have to find a new forwarder. If there were more than two sharers before replacement, then L2 remains in the SS state through move to SS path. But if there were exactly two sharers, then replacement leaves an exclusive copy and L2 again moves to empty through this path. In the final case, let's assume that one L1 has an exclusive copy and L2 is in the empty state. When that block is replaced, then L2 moves to the M state to indicate that no L1 cache has it. Now move to M, move to empty, move to SS, and move to SS forward are all internally generated events to the L2 cache controller based on sharer count calculations. Now Gem5 has a classic model which has a default coherency protocol based on MoEC, but that protocol is not configurable. Thus, we chose Ruby, which can model different cache hierarchies, different cache coherence protocols, as well as interconnects. Now, one such protocol called MESI 2 level is part of the Gem5, which we improved to incorporate the F state. It has private L1 caches and a shared L2 cache with a directory. The code for the cache and directory controllers are specified in .cc format, but their state machines are specified through a domain-specific language called as SLIC. Now, SLIC has several components like the TBE buffers. A TBE buffer is allocated when we start moving away from a stable state and is deallocated when we reach the next stable state. L1 and L2 caches communicate through coherence messages which are passed around using ports. For example, when L1 wants a read-only block, then it issues a getters request to L2. These messages are then used to generate events which initiate transitions between the states. And as part of the transition between the states, several actions are taken. Now, this code snippet provides a better explanation of the various SLIC components. So, for example, this keyword denotes a transition from state M to state I when it receives a forward getX event. As part of this transition between M to I, the following actions take place. Now, this forward getX event is triggered when we receive the appropriate request from the request L1 networking input. In this section, we present the results we obtained in simulation runs of parsec benchmarks. This sequence was extracted from the simulation logs, and it shows how a forwarder satisfies a getters request. So initially, L1 cache 6 is the forwarder, that is, it is in the F state, and the L2 cache is in the SS state. Now next, it receives a getters request from cache 4. That means cache 4 moves from I state to IF state after giving that getters request to L2. Also, the L2 cache moves from SS to SSMBTR on getting that getters request. Now, once L2 receives the request, it forwards the request to the forwarder, that is cache 6. And we can verify that from the destination vector that the destination for that forward getters is cache 6. Upon receiving the forward getters, the cache 6, which was originally in F state, moves to the S state, and it sends the data to the requester. Cache 4, upon receiving the data, sends unblock to the L2 cache. Upon receiving the unblock, L2 cache moves from SSMBTR back to the SS state. Also, the requester, that is cache 4, has moved from IF state to F state. So after all these transitions, L2 cache adds the cache 4 as in the sharer list. So we can see that initially cache 4 was not available in the sharer list and gets added once it receives the data. Also, the new requester, our L1 cache 4, becomes the new forwarder. This is another coherence transaction example which involves forwarding. So initially L1 cache 3 issues L1 replace request to L2 cache and deallocates its block. And next L1 cache 6 issues L1 replace request to L2 cache and deallocates its block. Because of serialization, the request from L1 cache 3 is serviced first. So this is the initial sharer's state associated with the L2 cache. So you can say that L1 cache 3, 4, 5 and 6 are the original sharers, and cache 3 is the forwarder. Thus, the same cache 3, which is the forwarder, is getting replaced, and we need to find a new forwarder. So first of all, L2 receives the L1 replace request from cache 3, and then it issues a become forward request to the next immediate sharer. In our case, since L1 cache 3 is getting replaced, the next immediate sharer is cache 4. Thus, finally, the cache 4 becomes a forwarder, and also it is added, and also the L3 cache is removed from the sharers list.